In heliocentric terms, Three Eyes Atlas is a hyperbolic interstellar object with an eccentricity exceeding unity. Its trajectory defined by a velocity vector that ensures it will not be gravitationally captured by the Sun. Its inbound velocity, measured in the reference frame of the solar system barycenter, reflects the kinetic energy acquired from ejection processes in its parent stellar system. Processes that may have involved close encounters with giant planets or stellar dynamical instabilities. Observations of its nucleus suggest a sub-kilometer-to-kilometer scale body composed primarily of refractory silicates, volatile ices, and carbonaceous compounds, encapsulating primordial material from an extrasolar protoplanetary disk. The cometary tail, a composite of ionized gases and dust particles, is sculpted by the interplay of solar radiation pressure, the heliospheric magnetic field, and anisotropic outgassing from the nucleus. In the latest NASA images, we observe a temporal evolution in the tail morphology. Dust jets exhibiting non-radial components. Ion tail segments showing curvature indicative of interaction with the solar wind's Parker spiral structure. Forward-pointing features, or anti-tails, emerge as a projection effect resulting from the intersection of Earth's line of sight with the orbital plane of ejected particulate matter, revealing the three-dimensional kinematics of dust grains varying in beta parameter, the ratio of radiation pressure to gravitational force. Spectroscopic analyses, though limited due to solar conjunction, suggest an enhanced Keoch-Stano ratio, with carbon monoxide sublimation dominating at heliocentric distances, where water ice remains largely inert. The high volatility of CO and Cl at distances of several astronomical units generates asymmetric outgassing, forming collimated jets that perturb the momentum vector of the nucleus, producing measurable non-gravitational accelerations. These accelerations, modeled using the standard Marston-Sekanina formalism, must account for sublimation, driven forces, and potential torques, which in turn influence the evolution of the tail's geometry and the comet's spin state. The heliocentric obscuration presents a unique observational constraint. During solar conjunction, Earth-based photometry is impossible due to the glare, yet instruments such as SO-ECA-LASKIO and the ESCARO heliospheric imagers can capture scattered light from the dust coma, revealing changes in brightness and asymmetry. By analyzing phase, angle, dependent scattering and forward scattering enhancements, astrophysicists can infer particle size distributions, mass loss rates, and the temporal variability of ejection events, constructing a near, continuous time series of activity, despite the apparent invisibility from terrestrial vantage points. Three-Eyed Atlas's nucleus is hypothesized to be irregular, its rotation period potentially on the order of several hours, leading to diurnal modulation of sublimation-driven outflows. The anisotropy in active regions produces jets preferentially directed along spin-axis vectors, further complicating tail morphology. Modeling of dust grain dynamics incorporates the canonical Whipple model, extended to account for non-spherical particle shapes, differential solar radiation pressure, and Lorentz force coupling for charged grains within the solar wind plasma. These calculations predict tail divergence, filamentation, and curvature that are consistent with the observed morphological evolution in recent imagery. From a dynamical perspective, the comet's hyperbolic excess velocity suggests a low probability of planetary encounters, yet even minute gravitational perturbations can induce measurable changes in trajectory over interplanetary distances. The secular evolution of the orbit, driven by non-gravitational accelerations and minor planetary perturbations, is monitored to refine ephemerades for predictive modeling once Three Eyes Atlas reemerges from solar occultation. Such predictive capability is critical not only for observational scheduling, but also for understanding the transfer of interstellar material into our solar system environment, a process with profound implications for comparative planetology and the study of exogenous organics. The tail composition is a direct diagnostic of primordial chemical reservoirs. Observations of molecular emission lines, particularly CN, CLC, and OH, allow the reconstruction of photodissociation pathways and sublimation thermodynamics. The detection of CO dominated outgassing at heliocentric distances of 3 to 4. A U implies the retention of hypervolatile species that would have been lost during early stellar irradiation phases, offering insight into the thermal history of the progenitor system. Such retention suggests low density regolith and minimal thermal metamorphism, consistent with a dynamically ejected object that spent billions of years in the cold interstellar medium, shielded from significant radiative processing. Ion tail dynamics reveal additional complexity. The interaction with the solar wind, a magnetized plasma streaming radially from the Sun, imparts velocity components perpendicular to the nucleus-Sun vector. Charge exchange processes, photoionization, and magnetic reconnection events shape the ion tail into striated structures, observable in space-based coronagraph imagery. Variations in solar wind density and speed induce transient features, allowing astrophysicists to probe the coupling between small, body outgassing and heliospheric plasma physics, a natural laboratory for magnetohydrodynamic processes. Despite the observational hiatus due to solar occultation, models incorporating radiative transfer, particle scattering, but in plasma interactions allow reconstruction of the comet's activity profile. These models simulate coma density, tail particle trajectories, and brightness fluctuations, providing a virtual dataset to compare against future observations post-conjunction. By integrating heliocentric geometry, rotational dynamics, and outgassing physics, the predictive framework for 3I's atlas becomes increasingly robust, allowing a near, continuous monitoring of a body temporarily hidden behind the Sun. In this context, 3I's atlas exemplifies the intersection of multiple astrophysical disciplines: celestial mechanics, planetary science, astrochemistry, plasma physics, and observational astrophysics converge to interpret the fleeting signals of an interstellar visitor. Its changing tail is more than an aesthetic feature. It is a laboratory for understanding hypervelocity object, solar wind interactions, dust-grain dynamics under variable radiation pressure, and the preservation of primordial molecular reservoirs across light years of interstellar transit. Even in solar obscuration, anticipation builds for the comet's post-conjunction observability. As 3I's atlas emerges from behind the solar disk, telescopes will measure changes in tail length, curvature, and color indices, while spectroscopy will reveal any compositional evolution due to solar heating. Variations in non-gravitational acceleration, spin rate, and jet activity can be compared to pre-conjunction observations, validating theoretical models and refining our understanding of interstellar cometary physics. The narrative of 3I Atlas, rich in hyperbolic orbital dynamics, non-gravitational effects, and compositional anomalies, is a testament to the interconnectedness of cosmic processes. Each sublimated molecule, each ionized particle, and each dust grain follows the laws of physics that govern the galaxy. Yet the specific configuration observed during solar conjunction is unique. A transient phenomenon captured in photons before they reach our detectors, revealing the interplay of forces that shape small bodies at the frontier of the solar system. The interstellar origin of 3I's Atlas situates it within a category of hyperbolic bodies, whose trajectories are defined by kinematic energies, exceeding the gravitational binding energy of the Sun. Its inbound velocity, measured relative to the local standard of rest, implies ejection from its parent system at velocities consistent with planetesimal scattering events, perhaps through gravitational interactions with a giant planet or through multi-body instabilities during early stellar evolution. The preservation of hypervolatile species within its nucleus, including CO, Sol, and possibly NO, implies that the object has spent the majority of its lifespan in temperatures below 30 Kelvin, avoiding radiative processing or thermal alteration that would otherwise deplete such species. The nucleus itself, inferred through light curve analysis and high-resolution imaging, is likely an irregular, low, orbital body with a heterogeneous surface. Morphological irregularities, including ridges, depressions, and possibly a bilobed structure, suggest formation processes akin to accretional coalescence in a low-density protoplanetary disk, punctuated by collisional events. The rotational dynamics of the nucleus, subject to torques from asymmetric outgassing, result in a complex spin state that modulates the temporal and spatial distribution of sublimated material. Observed jet structures emerge from active regions that may correspond to localized pockets of hypervolatile ices, producing anisotropic thrust vectors that slightly perturb the hyperbolic trajectory in measurable ways. The comet's tail, divided into the dust tail and the iron tail, is an intricate interplay of physics. Dust particles, varying in size from sub-micron to millimeter scales, respond to solar radiation pressure in proportion to the beta parameter, resulting in curved trajectories that project into the anti-tail phenomenon when viewed from Earth. Forward, scattering enhancements at high phase angles produce apparent brightness amplification, revealing fine, scale structures within the tail that are otherwise invisible. Meanwhile, ionized species, dominated by CO, XO, and CN, are entrained along heliospheric magnetic field lines, forming the ion tail with characteristic striations aligned with the interplanetary magnetic field. Variations in solar wind density, velocity, and turbulence-induced transient bending and kinks in the iron tail, effectively encoding a record of solar plasma conditions in the morphology of the comet. The solar conjunction of 3i Atlas imposes both observational and interpretive challenges. From Earth, the comet's proximity to the Sun prevents direct photometric and spectroscopic measurements, yet spaceborne coronagraphs and heliospheric imagers offer an indirect window. Instruments such as SOCAUG, LASCO, STERO-A, and STERO-B capture scattered sunlight from coma and tail particles, allowing astrophysicists to derive particle size distributions through scattering analysis, as well as to estimate mass loss rates by integrating brightness profiles with assumptions of albedo and phase function. Forward, scattering geometries during conjunction produce enhanced brightness for small dust particles, enabling refined inferences of size. Frequency distributions, a key parameter for understanding nucleus activity. Sublimation chemistry drives the observable features of the comet. At heliocentric distances of 203 AU, water ice remains marginally active, while hypervolatiles like CO and SIL sublimate at significantly lower temperatures, producing collimated jets that dominate the morphological evolution of the tail. These jets generate anisotropic momentum transfer, producing non-gravitational accelerations quantifiable through the Marsden-Sekanina formalism. Variations in acceleration can be temporally correlated with rotational phase, revealing the location and relative activity of discrete volatile reservoirs on the nucleus. The interplay between rotational dynamics and jet activity also affects the coma. As the nucleus rotates, active regions alternately face toward and away from the Sun, modulating sublimation flux. This diurnal cycle produces a periodic variation in coma brightness, detectable in precise photometric measurements. The resulting coma asymmetry contributes to the curvature and filamentation observed in the dust tail, as smaller grains experience differential acceleration due to radiation pressure. Numerical simulations of particle dynamics, incorporating gravitational perturbations, solar radiation forces, and the Lorentz force on charged grains, reproduce the complex tail structures observed in the most recent images. The iron tail provides a complementary diagnostic. Charged particles generated via photoionization and charge exchange are entrained by the solar wind, which flows radially at velocities between 300 and 800 km, depending on heliolatitude and coronal conditions. The Parker spiral configuration of the interplanetary magnetic field imposes a characteristic curvature on the iron tail, while temporal variations in solar wind density create knots, discontinuities, and oscillations in tail structure. High-cadence observations from spaceborne instruments allow measurement of these dynamics, effectively turning 3i's Atlas into a probe of heliospheric plasma conditions during solar conjunction. Comparative studies with prior interstellar objects, notably 1Z Oumuamua and 2I's Borisov, provide context for understanding 3i's Atlas, unlike the elongated, apparently inactive Oumuamua, which displayed no detectable coma, or the volatile, rich Borisov, which exhibited typical cometary activity with a relatively stable tail. 3i's Atlas demonstrates complex tail morphologies with transient forward, pointing structures. These differences may arise from compositional heterogeneity, nucleus size, surface activity, and exposure to radiation in the interstellar medium. By analyzing tail evolution in conjunction with heliocentric distance and phase angle, astrophysicists can infer physical parameters of the nucleus, including density, tensile strength, and the distribution of volatile compounds. The physical properties of the dust grains are crucial for understanding tail dynamics. Grain sizes dictate their response to radiation pressure, while composition affects albedo, sublimation rates, and interaction with the solar wind plasma. Carbonaceous particles, silicates, and icy grains each contribute differently to the observed brightness, polarization, and thermal emission. Multi-wavelength observations, including visible, infrared, and ultraviolet, provide complementary constraints on grain properties, enabling a detailed reconstruction of tail composition and structure. Solar heating during conjunction also induces thermophysical effects on the nucleus. The near side exposed to solar flux experiences temperature gradients that drive thermal fracturing, surface erosion, and sublimation, driven outgassing. Thermal modeling predicts localized stress fields, which may result in micro-fracturing or the exposure of new volatile, rich layers. These processes not only influence outgassing rates, but also produce measurable changes in spin state and non-gravitational acceleration vectors. Over the course of the comet's passage through the inner solar system, these effects accumulate, subtly altering the nucleus's rotational dynamics and surface morphology. The mass loss rate, a critical parameter in cometary physics, can be inferred by integrating tail brightness and modeling the particle velocity distribution. For three-eyed atlas, preliminary estimates suggest episodic enhancements correlated with jet activity, likely associated with volatile, rich regions or transient surface fractures. Dust-to-gas ratios derived from spectroscopic and photometric data indicate a predominance of micron-scale grains, consistent with observed forward, scattering features and anti-tail projections. By combining these observational constraints with dynamical modeling, astrophysicists can estimate total mass lost during the solar encounter, providing insight into the long-term evolution and survival probability of interstellar objects traversing the solar system. Magnetohydrodynamic interactions between the cometary ion tail and the solar wind also encode valuable information. Charged species interact with the interplanetary magnetic field, producing alpha-Nic disturbances, tail disconnection events, and striated structures aligned with magnetic field lines. Observing the morphology and dynamics of these features allows indirect measurement of local solar wind parameters, including density, velocity, and magnetic field orientation. In this sense, Three-Eyes Atlas functions not only as a relic of interstellar space, but also as a natural probe of heliophysical phenomena. As the comet gradually recedes from solar conjunction, predictive modeling anticipates the reemergence of distinct tail features observable from Earth. Numerical simulations suggest continued curvature of the dust tail, potential bifurcation into multiple filaments, and a gradual realignment of the ion tail along the updated Parker spiral trajectory. Monitoring these changes will enable the validation of models that incorporate rotationally modulated outgassing, anisotropic dust ejection, and solar wind coupling, providing a comprehensive understanding of the physical and chemical evolution of an interstellar object under solar influence. The heliospheric environment surrounding Three-Eyes Atlas during solar conjunction is a dynamic and complex plasma system, characterized by the constant outflow of charged particles from the Sun and structured by the Parker spiral magnetic field. As the comet's ionized species interact with this plasma environment, they experience electromagnetic forces that dictate the formation and evolution of the ion tail. Photoionization of neutral gases, particularly CO, HNO, and CN, produces ions that are then entrained along magnetic field lines, forming elongated plasma filaments that extend millions of kilometers from the nucleus. Temporal variations in the solar wind velocity, density, and magnetic field orientation produce oscillations, striations, and even disconnection events within the tail, creating a dynamic record of heliospheric conditions encoded in the morphology of the plasma. The dust tail, though neutral, responds indirectly to heliospheric forces through radiation pressure, which imparts accelerations inversely proportional to particle size. Larger grains with lower beta parameters follow trajectories close to the nucleus orbit, forming the classical curved dust tail. Smaller grains, in contrast, are accelerated more strongly by solar photons, producing extended fan-shaped structures that appear to point away from the sun. Forward scattering phenomena, particularly at high phase angles during conjunction, enhance the brightness of these micron-scale grains, enabling indirect observations that allow the reconstruction of particle size, frequency distributions, albedo, and composition. Spectroscopic observations, although limited by solar glare, provide crucial insights into the molecular inventory of Three Eyes Atlas. Hypervolatile species such as CO and Shal dominate sublimation, driven activity at heliocentric distances beyond 2 AU, while minor species including NHE, CH, and possibly organic molecules are detectable in sensitive infrared or ultraviolet bands. Emission lines from radicals such as CN, and CW reveal photodissociation pathways initiated by solar ultraviolet radiation, which fragment parent molecules into daughter species that populate the coma and contribute to tail formation. By analyzing the relative abundances of these molecules, astrophysicists can infer the thermal history and chemical evolution of the nucleus, linking observed activity to primordial conditions in the parent protoplanetary disk. Radiative transfer modeling is essential for interpreting brightness variations observed during solar conjunction. Coma density, optical depth, and particle scattering phase functions are integrated to reproduce observed light curves and tail morphologies. Forward scattering enhancements, scattering efficiencies, and anisotropic dust emission all contribute to complex brightness patterns, which can be deconvolved to estimate mass, loss rates, particle size distributions, and the spatial distribution of active regions on the nucleus. These models, validated against space-based coronagraph imagery, provide a quantitative framework for understanding the interplay between physical processes and observational geometry. The rotational dynamics of the nucleus, influenced by outgassing torques, are critical for interpreting temporal variations in coma and tail structure. As the nucleus rotates, active regions alternate in solar illumination, producing episodic jets that can shift the center of mass and modulate spin rate. These rotational modulations manifest in tail morphology as periodic variations in filament orientation, dust column density, and ion tail curvature. High-fidelity simulations incorporating nucleus shape, rotational axis, and jet activity allow the prediction of these features, which can then be tested against observational data once the comet emerges from behind the sun. From a dynamical perspective, Three Eyes Atlas represents a rare case study in hyperbolic object, solar system interaction. Non-gravitational accelerations induced by asymmetric outgassing introduce small but measurable deviations from a purely Keplerian trajectory. These accelerations, parameterized through the standard Marsden-Sekanina formalism, must be accounted for when predicting post-conjunction ephemerides. By combining observational constraints with orbital mechanics, astrophysicists refine predictions of tail orientation, nucleus position, and potential close approaches to planetary bodies, although the probability of significant planetary interaction remains extremely low. The isotopic and chemical composition of Three Eyes Atlas offers profound implications for comparative planetology and astrobiology. Ratios of N/CBC, N and DDH provide constraints on the formation environment and evolutionary history of the object. Elevated DDH ratios in water ice, for example, suggest formation in cold, distant regions of a protoplanetary disk, consistent with its hypervolatility and low thermal processing. The presence of complex organics, inferred through infrared spectroscopy and photodissociation analysis, implies that interstellar comets can deliver prebiotic compounds across stellar systems, enriching our understanding of chemical universality and the potential for life bearing molecules beyond the solar system. The interplay between thermal physics and sublimation chemistry shapes the nucleus surface. Temperature gradients induced by solar irradiation during conjunction produce differential sublimation, thermomechanical stresses, and microfracturing. These processes expose new layers of hypervolatile ices, triggering secondary outgassing events that alter tail morphology and non-gravitational acceleration vectors. Over time, cumulative sublimation and thermal erosion reshape the nucleus surface, modulating subsequent activity and influencing long-term evolution as the object recedes into interstellar space. Observational comparisons with previous interstellar visitors reinforce the uniqueness of 3I's Atlas. Unlike 1Eu's Oumuamua, which exhibited non-gravitational acceleration without detectable coma, and 2I Borisov, whose tail structure was comparatively uniform, 3I's Atlas demonstrates dynamically evolving tail morphology with forward-pointing features, filamentation, and curvature consistent with complex dust, plasma, radiation interactions. This suggests a heterogeneous nucleus with localized volatile reservoirs capable of producing anisotropic jets and fine-scale dust structures observable even during solar conjunction. The comet's passage through the inner solar system also provides a natural laboratory for heliophysical studies. By monitoring tail curvature, striations, and disconnection events, astrophysicists can infer local solar wind parameters, magnetic field orientation, and transient heliospheric disturbances. In this sense, 3I's Atlas functions as both an interstellar messenger and a diagnostic tool, bridging planetary science and space physics. As it emerges from behind the Sun, 3I's Atlas is expected to reveal post-conjunction changes in tail morphology, brightness, and composition. Predictive models suggest continued anisotropic dust emission, potential bifurcation of the dust tail, and realignment of the iron tail along the updated Parker spiral configuration. These observations will allow validation of rotationally modulated outgassing models, radiative transfer calculations, and dust-plasma interaction simulations. By combining these data, scientists will gain an unprecedented understanding of how interstellar comets respond to solar proximity and heliospheric forces. Ultimately, the study of 3I's Atlas is a testament to the interconnectedness of cosmic processes. From the chemical inventory preserved within its nucleus, to the dynamical imprint of non-gravitational forces, to the heliophysical phenomena encoded in its ion tail, every facet of this object offers insight into planetary formation, interstellar chemistry, and the evolution of small bodies across light years. Its transient visibility, punctuated by solar conjunction, underscores the challenges of observational astrophysics, while highlighting the ingenuity of instruments and models capable of reconstructing its activity, even when hidden from direct view. 3I's Atlas serves as a bridge between solar system science and interstellar exploration. Its morphology, chemistry, and dynamics provide a template for understanding other hyperbolic objects, informing the design of future observational campaigns, spacecraft missions, and theoretical models. The comet's hypervelocity passage through the heliosphere allows astrophysicists to probe fundamental questions about the transport of material between stellar systems, the survival of hypervolatile ices in interstellar space, and the potential delivery of organic molecules to nascent planetary environments. In essence, every photon captured from 3I's Atlas carries the imprint of cosmic history. Dust grains accelerated by radiation pressure, ions entrained in solar wind plasma, and sublimated molecules glowing under ultraviolet excitation are all messengers from a distant system, traversing light years to inform our understanding of planetary formation, chemical evolution, and the dynamics of interstellar space. Even in moments of solar obscuration, predictive modeling, radiative transfer calculations, and heliophysical simulations allow humanity to read the narrative encoded within this celestial traveler. As the comet continues its journey, leaving the inner solar system behind, it will eventually recede into the depths of interstellar space, returning to the cold void from which it came. Yet the observational legacy it leaves behind, comprising tail morphology, chemical composition, rotational dynamics, and heliophysical interactions, will remain a rich source of data for years to come. Scientists will continue to analyze brightness fluctuations, tail structures, and spectral lines, piecing together a detailed portrait of an object that serves as both a messenger from another star system and a natural laboratory for understanding the interplay of forces shaping small bodies in our own solar system. As 3-Liza Atlas completes its fleeting journey through the inner solar system, retreating inexorably toward the interstellar void from which it originated, one cannot help but reflect on the scale and profundity of its passage. It is a reminder that the solar system is not an isolated environment, but part of a vast galactic ecosystem where matter circulates across light, years, where chemical and dynamical processes transcend stellar boundaries, and where small bodies such as this comet act as messengers bridging the distances between star systems. Each dust grain, each ionized molecule, each photon emitted from the coma is a record of history older than the Sun itself, a preserved narrative from a protoplanetary disk orbiting a distant star billions of years ago. The observational legacy of 3I's Atlas is extraordinary. Despite its temporary concealment behind the solar disk, predictive models, radiative transfer simulations, and space-based coronagraph imagery allowed scientists to reconstruct its activity with remarkable fidelity. The tale, ever-changing and intricate, serves not merely as a visual spectacle, but as a dynamic laboratory, where radiation pressure, solar wind interactions, and anisotropic outgassing converge to produce structures that encode physical laws in their curvature, brightness, and motion. Forward-pointing filaments, antic-tail projections, and filament bifurcation are not anomalies, but signatures of the complex interplay between heliospheric physics and the comet's intrinsic properties. In the chemical domain, 3I Atlas offers a rare glimpse into the inventory of an extrasolar planetesimal. Hypervolatile ices such as CO and Kel, supplemented by trace organics and photodissociation products, have survived interstellar transit for billions of years, unaltered by thermal processing or radiation exposure sufficient to erase their primordial character. The presence of these compounds challenges models of cometary evolution and enhances our understanding of molecular preservation in low-temperature environments. Isotopic ratios, volatile abundances, and organic chemistry hint at processes operating in distant protoplanetary disks, allowing comparative studies that enrich our understanding of planet formation, chemistry, and the distribution of prebiotic molecules across the galaxy. The dynamical signatures of 3I's Atlas are equally revealing. Non-gravitational accelerations, induced by localized sublimation jets, perturb the hyperbolic trajectory and reveal the subtle yet measurable impact of outgassing on small bodies. Rotational modulation, torques from asymmetric mass loss, and interactions with solar radiation pressure produce observable changes in tail morphology that can be precisely modeled. Through these observations, scientists can deduce nucleus properties, including shape, density, and surface heterogeneity, while simultaneously probing the response of interstellar bodies to solar system forces, a rare opportunity to study physics that otherwise remains theoretical. From a heliophysical perspective, the comet has become a proxy instrument for studying the solar wind, magnetic field interactions, and plasma dynamics. Its iron tail, shaped by electromagnetic forces, responds to temporal variations in solar wind density, velocity, and turbulence, producing oscillations, striations, and even transient disconnection events. Observing these features provides indirect measurements of heliospheric conditions during solar conjunction, offering insights into magneto-hydrodynamic processes that affect not only comets, but also the broader space environment in which Earth itself resides. In essence, 3I's Atlas becomes both subject and tool, revealing the interplay between small body physics and solar phenomena. The transient nature of this encounter highlights the fragility and ephemerality of observational opportunities in astronomy. A small shift in trajectory, a change in brightness, or the temporary concealment behind the Sun could have rendered 3I's Atlas invisible to modern instruments. Yet, through careful modeling, predictive simulation, and the integration of multi-wavelength observations, humanity has captured a comprehensive portrait of an interstellar traveler. In doing so, we extend our ability to study objects that exist beyond the boundaries of our solar system, turning fleeting encounters into lasting knowledge. As three-eyed Atlas recedes, the implications of its passage extend beyond immediate observation. Interstellar comets act as vehicles for the transport of matter and organics between star systems. They demonstrate that chemical evolution, the formation of complex molecules, and the preservation of primordial material are not unique to our own sun, but are universal processes occurring throughout the galaxy. Each interstellar visitor thus represents a chapter in the ongoing narrative of cosmic evolution, connecting stars, planetary systems, and ultimately, the potential for life across the cosmos. In the broader context, Three-Eyed Atlas challenges humanity to think beyond the solar system, to consider the galaxy not as an abstract collection of distant stars, but as an interconnected system where small bodies traverse interstellar space, carrying with them the chemical fingerprints of their origins. These objects remind us that our understanding of planetary science, chemistry, and astrophysics is incomplete without incorporating the influence of extrasolar materials. Observations of interstellar comets, like Three-Eyed Atlas, thus provide the empirical foundation for theories of galactic chemical distribution, interstellar transport of organics, and the universality of the physical laws that govern planetary system formation. In the narrative of Three-Eyed Atlas, there is also a human story, a testament to ingenuity, persistence, and curiosity. From the initial detection using survey telescopes to the high-resolution imaging by spaceborne coronagraphs, from photometric modeling to heliophysical analysis, humanity has marshaled the full spectrum of astrophysical tools to capture and interpret this visitor. Every observation, every calculation, but every simulation reflects the collaborative effort of a global scientific community dedicated to understanding the universe and our place within it. Even as the comet vanishes beyond the reach of observation, its legacy endures. The data collected will inform the study of future interstellar objects, guide the design of spacecraft missions aimed at intercepting hyperbolic bodies, and enhance our understanding of the dynamic, evolving universe. Three-Eyed Atlas is more than a comet. It is a bridge between worlds, a carrier of primordial history, and a harbinger of the possibilities that lie in the exploration of interstellar space. Ultimately, the story of Three-Eyed Atlas is a reminder of our cosmic perspective. The sun, the planets, and humanity itself are but small actors on a vast galactic stage, where interstellar objects trace silent arcs across light years, bearing chemical and dynamical records of distant star systems. Each encounter, no matter how brief, illuminates the processes that shape planetary systems, preserves the chemistry of pre-solar environments, and inspires reflection on the interconnectedness of all matter in the galaxy. Three-Eyed Atlas, in its transient brilliance and ephemeral presence, exemplifies the majesty, complexity, and wonder of the cosmos, a reminder that even the smallest celestial wanderer can expand the horizons of human knowledge and imagination. As it retreats, leaving only its changing tale etched in the records of our instruments and the minds of those who observed it. Three-Eyed Atlas completes a journey that began far beyond the sun, spanning billions of kilometers and millions of years. It carries with it the history of another star, another system, another place in the galaxy, offering us a fleeting yet profound glimpse into the processes that govern planetary formation, interstellar chemistry, and the distribution of matter across the cosmos. And though it will fade from view, the scientific and philosophical insights it provides will resonate for generations, a testament to the power of observation, the universality of physics, and the boundless curiosity that drives humanity to look up and ask not only what lies beyond, but how it connects to us here on Earth.